share some link here so that you can today itself can go to IBM platform and run code. So we have all the tutorials already available in the platform. So you don't need to wait for me for tomorrow. After just my session, please visit to this website from IBM. I just shared the link here. Please go ahead with the link. And after this session, you can just apply the theory. Okay. As I always prefer to take some of the mathematical aspects because that's the easiest language one can explain our what is happening in our mind, what we want to do. Otherwise, if it is literature, it's difficult to understand, right? Uh, so yeah. So let us start with certain things because all these topics that I'll be covering today and tomorrow, that is quantum Fourier transform, the quantum phase estimation, source algorithm, right? Source factoring algorithm, and the HHL algorithm for solving linear system of equations. So they all are related. And why I chose these topics, because if you learn the very first topics, so the next and onward topics won't be difficult for you. Right. So I'll start with the source factoring algorithm, but before that, because some of you may be joining in this QT-05 as a fast course, so I'll appreciate even your effort and your interest and curiosity to join this course. So so let's start with certain very basics things for 5 minutes, and then we'll come back to the actual thing, right? So recap certain quantum computing things. What we know, that there are two things, right? What we have learned for now, those okay. Uh, leave about the quantum information theoretic part, just simple computing part. What we have learned, that qubits are states or vectors, or sometimes we call state vectors. Okay, and the um, operators in quantum mechanics or quantum computing, they are matrices, right? So we need to learn, if you want to understand quantum computing, just you have to appreciate our this UG understanding or postgraduate understanding of vectors and matrices and their properties, right? So let us recap certain things so that we know, just a recap. So Ket 0, so because any quantum state Ket psi, we typically represent with the certain basis system, right? Any vector, if you want to write, like for example, x vector, we write from our childhood, we write as 2 I cap plus 3 j cap. Along x-axis, it has 2 unit distance. Along y-axis or j-axis, it has 3 unit distance. Likewise, so these I and j are orthonormal vectors, so their dot product equals to 0, and individually their norm is equals to 1, right? That is what we have learned in our class 6 physics or class 7 level physics, right? So just apply that knowledge, that if quantum state or quantum wave function, whatever we say, wave function or state vector, right? Quantum information, even you can say, it is a vector quantity and it needs two basis system to represent, say, Ket 0 and Ket. If you write in this way, so it is equals to, say, alpha times Ket 0. So this basis system times a coefficient plus beta is another orthonormal basis times 1. This is what we learned, right? But Ket 0 is a vector 1 0, and Ket 1 is another just a orthonormal basis vector 0 1. Because if you draw, why I'm starting from this very basics, because just after this 2 hours class, you will learn a lot of things, how to implement circuits and all. And these are the first level principle, like just starting, always start with the basics things, right? So if you see in a two-dimensional Cartesian coordinate system, so this is the 0 0 point, this is the 1 0 point, this is the 0 1 point, right? This is the 0 minus 1, right? So this is minus 1 0 point, and this is your, say, 0 minus 1, right? And this 1 0 coordinate, we typically write in a vector form as, say, 1 0 this way, and this is this is we write as a vector of 0 1. Okay? So 0 1 is often in Dirac notation represented as Ket 1, And this 10 is written as a Dirac notation as Ket0. And that this is the same representation. These two are the same things. Right? That's why Ket0 and Ket1. They are simply column vectors, right? So this is the very basic things of what happening of quantum computing, right? So that's why Ket psi is just a column vector which is represented with orthonormal basis with a coefficient alpha and beta like this. And there are certain quantum postulates in quantum mechanics, right? Postulates. This is disturbing a lot. Just allow me. Quantum postulates, right? Like you, when you study probability theory, there are certain postulates or axioms. There is no proof of the axioms, right? So these are the axioms based on which things goes on, right? Like the other theories are built on. Similarly, quantum postulate, like every quantum mechanical phenomena, can be described with a wave function and it has a unit norm, right? So if you have a unit norm, right, and anything you do and you get suppose another quantum state, say get phi to get psi in another time and space, right? Suppose this is in particular time x1 and time t1, and after evolution of that wave function in x2 and t2, you get phi 2. Then also if you get phi 2, then phi 2 square norm should be also equals to 1, right? And this norm should be equals to 1. This is just the probability of that wave function, that if the wave functions look like this, whatever be the case, the total area under the curve, right, between these 2 points, say A to B, if fx is the representation of that wave functions, right, then integration of fx square dx A to B will be equals to 1. That's the probability law. And this is important because this is the probabilistic interpretation, and the same thing when we do on the quantum mechanical like linear algebra. So linear algebra, if we look at, then what I am telling, that norm of each vector psi should be equals to 1, whether it's the initial state x1 and t1 or it is in x2 state x2 t2, the norm should be equals to 1, right? Whether it is psi squared x or phi squared x, this should be equals to 1, right? And to make it happen that whether the earlier distribution was this and change distribution after certain mathematical algorithm you do, and you want the distribution like this, but overall the area should be equals to 1. Suppose the next probability distribution of the probability mass function in the discrete case, say it is g of x, right? Again, your integration g of x square dx equals to 1 from point say c to d. This will happen, right? This won't change. So hence, this is the unit complex unit vector. This is another complex unit vector, and this will only happen if there is a mathematical transformation that I get phi, which is a unitary transformation of the previous vector psi, right? Because the unitary transformation trace is preserved or the norm is preserved, right? Norm is preserved. So that means if I take the square of the second updated state, that is equals to u star u, right? U star u, and say psi star psi. This is the final state, right? So I will be getting some state like this because I have taken, I am assuming that the evolution is done by, or the transformation is done by some matrix U, but the condition is that it will be equals to 1 if it is psi star psi, because psi star psi was my initial state, that is equals to 1. It will happen if and only if u star equals to u, that is equals to u star u equals to identity, and that is a matrix which basically has this particular property. Also u star equals to u inverse you can write, okay, the same thing, they are equivalent. And this type of matrices are called the unitary matrices, right? Unitary matrices, right? And that's why all the quantum operations, quantum for especially for the physicists, it's for the isolated system. For computer scientists or engineers, it's just a transition matrix, right? So quantum evolution, whether you say it's a quantum evolution or it's a circuit, you can say or you can say it's an operator, okay, quantum operator, right? That is a unitary matrix, right? Unitary matrix, and that is basically your, in computer science we call it as a reversible logic. Reversible logic. So that is the basic fundamental of quantum computing, right? So now, why I am repeating these things to understand quantum Fourier transform? Because any algorithm you design, your ultimate goal is that you start, suppose, let us understand the classical part itself. What is your engineering system? You have a X input, you have a system, right? And you have an output Y. This is all about any engineering system, right? Here you have a K text as input. Any operations you do will be a unitary matrix, and you have an output state K2Y. That's the same thing, right? But how you design this U, because this U is special, it's a unitary matrix. It can be any engineering system, can be any matrix, but for a quantum circuit, it should be a unitary matrix, because to obey the quantum postulates, certain postulates are there, right? Whether it's a states, it's a evolution, it's a measurement for that. This is the situation, right? And overall, whether it's a quantum Fourier transform circuit, it's a quantum phase estimation circuit, it's a variational quantum eigensolver, it's a QAOA, it's a HHL, right? Whatever quantum algorithm it is, your goal is to design that U, right? That's the thing, this U matrix. Okay. So now this is about the certain postulates. Next, so we understand what state means now. States are vectors, right? And to represent vectors, we need certain orthonormal basis. Orthonormal basis. And here the orthonormal basis are computational basis, Ket0 and Ket1 for one qubit system. For multi-qubit, it can be multiple such 0 to multiple such 1, right? So for n number of levels or n number of qubits, how many states I can create? I can create 2 to the power n possible states, right? For example, if there are 2 qubits, how many computational basis I have? 0, 0, 0, 1, 1, 0, 1, 1. 4 possible basis states are there. And my quantum state can be a plane, or basically a hyperplane, which is a basically combination of all these 4 orthonormal basis vectors, right? So it's the 4. So if I create a, say, for example, 4-dimensional space, so this is not exact 4-dimensional space, just I'm drawing. Suppose I assume that there are 90-degree between all of them, like each between them, right? So suppose this is 0, 0, suppose this is 0, 1, 1, 0, and 1, 1, right? And your quantum state can be somewhere, right? Which is alpha times 0, 0, alpha 0, say alpha 1 times 0, 1, plus beta 1, say alpha 2 times 1, 0, and say alpha 3 times 1, 1. So you have 4 coefficients and 4 orthonormal bases, right? What is the objective of your Fourier transform? Normal Fourier transform. So you have a basis system, say time domain, and you are going to frequency domain, right? Or you have domain A, you are going to domain B. Domain A to domain B, where this time and frequency are the non-commutating operator, right? Non-commutating operator, or the domain A and domain B are non-commutating, right? That's why if there is, suppose this is flat in time domain, right? So suppose this is your X and this is your Fx, right? So this is flat in X domain, right? Okay. So that means if there are 2 points I choose, say this is x1 and this is x2, right? So there is no certainty of fx between x1 and x2, right? It is highly distributed, right? So this is highly basically uncertain in x, right? Now if I have a tool, right, maybe Fourier transform of certain mathematical tool, where I change this same thing with a mathematical transformation called kernel, right? For example, for Laplace transform it is e to the power st, for Fourier transform e to the power minus omega t, and so on, right? For wavelet, this has a different definition of kernel, right? and I go to some other domain, say x to y, say this is y, and my f of x become f of y, right? Where this has certainty, because it this way you cannot be certain where my fx is between x1 and x2. This is highly distributed, right? So it can be anywhere. It can be here, here, here. So it's a flat, right? Even if I draw this distribution like this, sinusoidal for now, right? So even if it is sine omega t versus t, right? So if I say like, what is the certainty of these functions between this and this? It can be here, 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 right? It is highly uncertain in time, uncertain in t, right? But if I look at this particular function, so this peak to this peak, it has a fixed lambda, right? If it has a fixed lambda, that means, so we know that v equals to nu lambda, right? Velocity equals to nu lambda, right? Or c equals to nu lambda, you can write for light specific case. So nu equals to your frequency, I can write f and lambda, right? So if I multiply 2f, so 2 pi c equals to 2 pi f lambda, right? So this 2 pi f is your angular frequency omega. So I can write it as omega lambda equals to 2 pi c, right? So from here, you can look at that. If I know the basically, if I know basically lambda, if I have certainty in lambda, or you can write basically omega equals to 2 pi c by lambda, right? So if you have certainty about lambda, you can tell about certainty in omega, right? So delta lambda is basically has certain relation with delta basically lambda, right? So even if you have uncertainty in omega t, but you have certainty in omega. So do you have a mathematical transformation that convert this signal or this particular function sine omega t to the omega domain itself, right? Or a f domain, because it's a basically omega equals to 2 pi f, right? So can you convert it to f domain such that I have highly certainty that I get a peak, and I can say okay, at f0 I get exactly the functional value, right? That may be say something I write at y of f, right? So that's the objective, how we look at a problem in original domain, and it has uncertainty when I present the definition of the thing, right? But I have a mathematical transformation such as like I defined this omega t, like for example, xt e to the power minus omega t. I convert this signal to a signal, right, where the representation is highly certainty. That means this omega and this time, they are basically non-commutating operator in physics, right? That's why you need the tool Fourier transform. This is the fundamental of Fourier transform, right? So similarly, what we have to do, we have a discretized version for this. This is a continuous version. We have a discretized version called DFT, discrete Fourier transform. And people got a matrix like this. So if you have a matrix like 1 omega, omega square, so on, then 1 omega square, omega to the power 4, so on, 1 omega cube, omega to the power 6, so on, like that, right? And this is called a basically Fourier matrix, DFT matrix, right? So the thing is that now similarly, what is happening when I'm representing in the discrete domain? So I have a certain coefficient, that means x0, x1, x2 of that xt, right? At different point, what are the values of the particular function, and I define them as a vector, say x vector, as these values. Actually, they are discretized in time, right? They are represented in the time basis or certain basis, x basis. And what I am actually doing after the Fourier transform, DFT or whatever you say, right? I'm getting some y, right? And I'm just changing the representation in other basis set where my basis is say f0 basis, f1 basis, f2 basis, and so on. So what I am exactly doing, by that I'm basically getting the vector y vector, so y0, y1, y2, yn minus 1, for example, right? This is my y. But how this y and how this x is related, suppose you are representing in this way, that this was suppose your original domain X vector, where X vector is basically alpha amounts of this, beta amount of this, gamma amount of this, and delta amount of this particular thing, right? Suppose X vector equals to your alpha, say X0 is your basis set, for example, or better, I should represent it with original coordinate system for now. So because many of you might have questioned what is the difference between DFT and QFT, discrete Fourier transform and quantum Fourier transform. So because I have some background in signal processing, so I think I should clarify this point. So suppose X0 coefficient times say I0 is your first basis, right? Plus this is your basis vector just. Then alpha 1 I1 is next basis vector. Say this is I0, this is I1, this is I2, this is I3, right? And say the next one is say alpha 2 I2 and alpha 3 I3, right? This is the representation of your X, right? Now this is a classical, this can be simply classical representation. And here, when you are representing your signal X to Y after the conversion with the definition, I'll come to the definition part later, right? But let us understand the philosophy. So when I'm just converting with the DFT matrix here, so what I'm getting Y0, Y1, Y2, and Y3 is my vector, right? How I'm getting this? So this is basically when I'm representing this this sequence together, right? So this is basically you can represent as, say, this coefficient will be changed. Say this is C0 times Fourier basis F0 plus C1 Fourier basis F1 plus C2 F2 and C4 C3 F3, right? And in terms of Fourier series representation, this F0, F1, F2, F3, these are trigonometric basis, right? Like sine and cos, right? And it can be any basis, any Fourier basis. Like in this particular case, I was giving an example. So if you look at this, can be your basis vector, right? In the row basis vector, otherwise you can look at this way, column basis vector like this, right? Like this, you can. So this is your F0, this is your F1, F2, and so on, right? Now, when you look at in the quantum computing part, now your signal X is represented as KTX, right? So when you represent it as a KTX, what you typically do is you represented your information with some probability amplitude P0 times the basis vector 0, 0, right? How you do the alpha 0 to P0? There are encoding scheme, amplitude encoding, basis encoding, there are techniques. But somehow you do, like alpha 0 to P0 you can do, right? This is possible. Then you converted this alpha 1 to say P1, for example, 0, 1 basis, computational basis, then plus P2, 1, 0, plus P3, 1, 1. So you are representing it as a vector P0, P1, P2, and P3. These are the probability amplitude of this orthonormal basis. That means this, and this. Suppose this is the case. Say this is your P0, P1, P2, and P3 of the basis 0, 0, 0, 1, 1, 0, and 1, 1. Right? And I need to design a quantum circuit because now my DFT should have a quantum mechanical design or quantum computing design, which is a unitary matrix. And naturally, Fourier transform DFT matrix itself is unitary. That's the good part. But the implementation is very different from the radix 2 implementation, butterfly structure representation that is there in the classical theory. Okay. So what I get typically is that now instead of this basis set 0, 0, 0, 1, 1, 0, 1, 1, I have a Fourier basis set. Say it is okay. The basis set can be say F0, Ket F0, Ket F1, Ket F2, and Ket F3. This is my representation. Okay. And my final vector Ket Y will be equals to C1 times this, or here you can write C1 tilde times this plus C2, C1 tilde times C0 tilde times this, C1 tilde times this plus C2 tilde times this plus C3 tilde times this. Just what has changed here? The changed thing is your original computational basis computational basis changed to Fourier basis, right? Fourier basis. Also, what had changed, this earlier probability distribution P0, P1, P2, P3 changed to C0 tilde, C1 tilde, C2 tilde, C3 tilde. That's all, right? And this and it was your one state representation, vector representation. This is another vector representation, and this basis representation you got using a unitary transformation of the previous one, right? So all we need to know before implementing Fourier series, this is some fundamental I thought to like correlate between the classical and the quantum part, right? Next is the measurement. This is important. Okay, so state we understand little bit we understand about what quantum state means from this discussion. Now let's understand operations. Operations also little bit we understand. Okay, operations are unitary matrices, and some of the operation in quantum from our QT other previous QTs we know that they are basically represented with quantum gates such as the Hadamard gate. So these are required to design quantum Fourier transform 1, 1, 1, minus 1. So now what remaining is that how to design this U, right? If we can design some U, we are done. How to design, I'll come. So because that U has to do with these quantum gates. So some examples of quantum unitary matrix, like unitary matrices in quantum or quantum gates are the Hadamard gates, which is a superposition gate, also represented as plus gate. Okay, the X gate, Pauli X gate, which is a rotation matrix about x-axis, 90-degree rotation matrix, right? Because any of the gate, if you do the X transpose X, it will be an identity matrix. If you do H transpose H, it will be an identity matrix. You can do by simple mathematical multiplication by hand, and you can check it whether they are at all unitary matrix or not. Okay. Now, so we represented state as alpha times 0 plus beta times 1, for example, in one qubit particular example. And one more basic introduction is required on the measurement. So to measure quantum state, suppose what is this particular probability alpha, you just need to do mathematical projection, right? So you get alpha back, and if you do basically inner product between this psi and the computational basis 1, you'll be getting the beta, because 0 and 0 are basically the same vector, right? The dot product will be 1, you will be getting alpha, because 0 and 1 are orthonormal, so dot product will be, so 0 and 0 will be equals to 1, and 0 and 1 will be equals to 0, right? Orthonormal vectors, because 0 and 1. So just apply this principle here with the dot product, you'll be getting alpha and beta, right? And additionally, alpha square plus beta square equals to 1 from probability postulate of quantum mechanics, right? This is we know. Another property I introduced that the quantum operation has to be unitary. That means U dagger equals to U inverse, that is equals to U star U, or U star equals to identity matrix, right? And there are some more properties we need to know, just determinant of U equals to 1, right? So because you are watching lots of lectures, so you may forget. So I'm just repeating these basics, and I'll come back to the implementation part. For a single qubit, unitary gates are typically rotation gates, right? On the surface of the Bloch spheres, for example, the Pauli gate. So if you have a quantum state here and you just want a theta degree rotation of the quantum state psi here, and you want just theta degree rotation of this quantum state from here to here, what you need to do, you need to multiply this vector with a rotation matrix like r theta psi, where r theta equals to your cos theta by 2 sin theta by 2. So minus sine theta by 2, and so sine theta by 2 and cos theta by 2. This is the quantum gate you need, right? So this is a r theta gate basically. This is also written as exp minus I theta by 2 y gates. Yes, so Pauli rotation gates embedded, right, with in the form of exponential form, and this is the particular quantum gate you need to apply here. So typically you initialize a qubit with state 0, then you apply a r theta gate. Basically, you encode the information to get it first as psi. Once you have the encoding here, then you apply a r theta gate and you get the phi state. This is your phi state, right? So this is like how you design the circuit. There are like few lines of codes only, 2-3 lines of codes. Okay. So now there are a few more things. Because quantum mechanics follows the eigen equations, like because this H psi equals to E psi equations you get from the Schrodinger equations, right? This is also important. And I just tell any quantum operations you want to do, that should be this particular operation on quantum should be unitary, right? To obey all other principle. So if I have a wave function, say ket psi, right, which is a eigen basically wave functions, better this can be any generic wave functions or quantum state, right? But there is a representation of the wave functions also possible, that it has an eigen state. For example, kx is the eigen state, right? If it is the eigen state, for example, then if h equals to u, then u ket x should be equals to some lambda ket x, same equation. So h psi equals to E psi. So basically H is an operator, energy operator. If you apply the energy operator on the wave function, you should get the energy quantity, which is a scalar quantity eigenvalue of that wave function taken as a represented as a eigenvector, right? The same scalar quantity here. There is one additional property on top of it. So suppose there are many such eigenvectors, say one of them is k, then you get a particular scalar k, right? Lambda k is a particular scalar that is an eigenvalue for the eigenvector, this one, right? Lambda k is the eigenvalue for the eigenvector this k. Now, if it is a unitary matrix, then modulus of all lambda k equals to 1. This is a property of the unitary matrix. Okay. Further, this lambda k is a complex quantity. You can represent as e to the power I theta, right? And then estimating the eigenvalue is related to estimating the theta, right? If you can estimate this theta, you are done. So this is an algorithm tomorrow we'll be studying called quantum phase estimation, QP, quantum phase estimations, right? And that is also related to QFT as well, right? And there is certain other phenomena in physics like degenerate state and all. So to get to individual states, so say lambda x is eigenvalue and lambda y is another eigenvalue, say lambda x. So this is one implications, and this is the second implication. So suppose lambda x not equals to lambda y, right? So if lambda x not equals to lambda y, right, then the corresponding eigenvector should be orthonormal. Okay, should be orthogonal with basically unit amplitude, or you can write it this way also. Their dot product equals to 0, right? Like this. So for this is some basics which are required, and we also understand because why this is so important, right? Now let's go to the like what is source algorithm and why I should study the quantum Fourier transform, right? Most likely 1994. Please, you can check the year. But there is also story, you can Google it, like YouTube, how the source factoring algorithm was discovered based on a research paper, where an author was trying to discover how to find out the periodicity of a function, right? And that paper got rejected by Sohr himself. And then later he realized this is an important piece of research work, and he continued and did his contributions for various encryptions and all, and finally discovered this factoring, which has a quantum advantage theoretical proof. And that's why it's so important, right? So what is Sohr factoring algorithm? And we'll slowly introduce the QFT, and tomorrow we'll see an implementation of that. So suppose you have a big number, and the big number is represented as n, right? N can be a, say for example, it can be a 2048 bit key. It can be like that, right? So when we transmit data from a point A to B, right, we have our data. Suppose this is the data, right? And you put an encryption on this such that no one can basically steal your data, right? And you put various cipher text on it, right? So encryption key. And suppose the key length is a big number, right? For a classical computer, it is hard to break this key number. So this number are designed in a way that it is a product of some prime numbers P and Q, right? So this P and Q are prime numbers, or sometimes P, we pick a number. So such that also sometimes how we design this way. So it's a big number chosen as as a factor of P and Q, but it is extremely hard to find out what P and Q are, these prime numbers, right? P and Q are the prime numbers. Okay, so basically how this source factoring algorithm works. So let me write a pseudocode for this, and implement it, because it's a fault tolerant algorithm, FTQC, fault tolerant quantum computing algorithm. So you cannot fully implement source algorithm, at least till we have the fault tolerant quantum algorithm. But some of the subroutines you can run on a quantum machine. For example, the fundamental subroutines for source algorithm is the quantum Fourier transform or the quantum phase estimations itself. So you can implement that on current hardware, right, up to certain limit. But the full-fledged applications of SOAR algorithm to really break certain encryption key is not the current capability of the current quantum machine, right? So your banking password is safe. Don't worry. Okay. So let me write certain the pseudocode part first, and then I'll come back to mathematical aspects. So I'm going a bit slow. I was too fast. So pick a number A that is co-prime, with n. With n means no common advisors, divisors. Okay, no common divisors. Okay, and then find the order R of the function a to the power R modulo n. Now you can ask me, what is this modulo? Why the power comes here? I'll explain with examples. Don't worry. Just let me write the pseudocode for this algorithm, and then I'll come back each and every point. Right. So this is equivalent to finding the smallest r such that a to the power r equivalent to 1 modulo n. Okay. Third is, if r is even, this is good in fact. Okay, this is good. If r is even, then x equals to a to the power r by 2 modulo n, and if x plus 1, so not equals to 0 modulo n, this is quite better in fact, then this P and Q, which are the factors of the number, right, n, contained in, or at least one right? Content in at least one of the GCD between greatest common divisor, right? Of x plus 1, comma n, and GCD this one. Else find another okay. So don't worry, like this at only if you look at this particular problem, and if you break this source factoring algorithm, what is the fundamental is you have a big number n, you want to prime factor which whose product is n, right? P and Q. So this has if you break this problem, this factoring problem, factoring of a big number into factoring into prime numbers, it has two components. One is finding the periodicity of number. Now you can ask me what is periodicity of numbers. I'll come to this point. Finding the periodicity of numbers, which is a exponentially complex problem. Periodicity of number, big number n, how the pattern is generated. And second is the modular arithmetic. So those who are not from computer science, for them, let me first explain what is modular arithmetic. Okay. And then we know that a good tool to find periodicity of a number is Fourier transform, right? So if I can find out what is periodicity of a number, I know the tool, right? And do I have a better tool? That is a quantum Fourier transform, right? So I'll come to this part. Now, if you just solve this problem, if you just try to solve this problem on a classical machine, let us first understand and appreciate the classical part itself. So what is the complexity of these two steps? So if you solve the simple factoring problem, right, on a classical machine for this two particular step, finding the periodicity and completing with a modular arithmetic for finding GCD and all, right? So the classical computation complexity is order of e to the power exponential, a constant time n to the power 1/3 log n to the power 2/3, right? This is the complexity, right? So this is roughly, I should not write this way because this is actual value will be very different. So write me this way. So this is you can write it is a roughly e to the power of n to the power something, right? So e to the power exponential. So if you have a key size, say key size of say typical key are 1024, 2048, and some of the like very important key are 4096, right? And if I write this now the key size, right, cipher key size, security key size to be say for example in 2 power, it's 2 power 10, 2 power 11, 2 power 12, right? Now on classical side, it is exponential power, right? Exponential power of n to the power something, right? And e to the power of this number is big, right? You can easily check that it's a very big number to basically break this into prime numbers. It's very uh, like complex problem. So that's why this RSA encryption is built on this principle that because it is exponentially hard to break a very high number of keys, right? That's why when you put a password in your mobile, in your bank, anywhere, 16-digit password or something, and they use that 16 digit to convert into certain big cipher key text, right? And they assume, okay, this is classically, it will take a very large amount of time to break it. So not possible, right? They have a fixed number of trials also. If somebody try for 3 times, 4 times, it will just lock that system, right? So similarly, here, it is RSA keys, like in terms of the time complexity is very exponentially hard to break, right? Now, once you apply the source algorithm, and this is also this particular method is with the best classical method. Okay, some SIP method, green SIP method, or certain SIP method. I forgot the exact name. If you apply the source algorithm here, the complexity boils down to order of n square log n log n, right? And this is roughly approximately order of n to the power 3, right? So that means if I have a key of 2 to the power 10, right? And if I encode the this information in qubits, basis states, so I need 10 qubits for now. If my information is represented in 10 qubits, the key, then I need 10 to the power 3, right? Which is basically some 1,000 qubits, error corrected qubits, right? This should be good quality qubits, to break the ciphertext. But we don't have a quantum computer of 1,000 qubits which are error corrected logical qubits currently. So your security or the is at least safe for the time being. But however, you can see the earlier complexity was exponential. Now it's polynomial, right? Polynomial. So e to the power something boils down to n square or n to the power 3, right? And this is a huge advantage in terms of the prime numbers factorizations. People are also searching for what are the better applications of this kind of algorithm to other things, like can I make an efficient frequency estimation technique, other things, right? So those are other things, but at least source factoring algorithm, it shows that it has good implications on the security in terms of the prime number factoring, right? So the problem of source algorithm is factoring a number, capital N, which is a product of two or more two prime numbers, and that is the basis which is the basis for security of our computers, security of our computers, right? For example, the RSA, right? RSA encryption technique. And those who are working, okay, what are the alternate technique that we can design where source factoring cannot break our key, right? We don't have a known quantum algorithm which can break those things, security. So those kind of sets of algorithm are known as PQC, or post quantum cryptographic key, right? I don't work on this area, so I don't have any knowledge. Just from the mathematical aspect, I'm just taking their names here. Okay. Okay, and I'm taking 5 minutes more before the break just to complete the modular arithmetic part, because this is for the non-computer science, computer science scholars. So modular arithmetic, let me cover, and then after the break, we'll come back with the QFT again. So in our schools, we have learned that 5 divided by 3. How did we do? 5, 3. So 1, 3, and 2 is the remainder, right? So it has a quotient. This is called a quotient, right? Quotient of 1 and remainder of 2, right? So any number we can divide with a bigger number or so, right? And this particular thing, it is written as 5 equivalent to, or 5 is written as 2. First you write the remainder part 2, then in bracket you write 2 modulo 3. right? So we don't write the coefficient quotient part. So if you divide 5 with 3, you have the remainder 2, right? So 5 is written as 2 modulo 3. This is the representation. So suppose I have a numbers set of numbers. I can write it as a sequence or as a set or as a vector, whatever you say, as 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? And I what I do, I suppose I have modulo 3, right? I want to divide with 3, right? So first of all, what will be the remainder, right? So if I do the modulo 3, so 1 will have the remainder 1, suppose. So for wherever I have 3, the remainder will be 0, right? 3, 6 will be 0 and 9 will be 0. 3 places I can easily divide with 3. 3 divided by 3 remainder 0, 3 divided by 6 remainder 0. Basically 9 divided by 3, I get the remainder 0. In other places, like 1 will have the remainder 1, 2 will have the remainder 2. Again, if it is 4, then basically 4 divided by 3, right? What will be the case? So 1, 3, I have 1. So 1 will come here. If it is 3, 5, I just did it. Like what is the remainder? 2. 2 will come here. Then if I divide 6 with 3, remainder will be 0. For 7, again, I will have 1, 2, 0, so on. So this is I got with modulo 3, right? Now, if you look at this number, this is repeated in every three, like every three component. When I divide the number x with modulo 3, I got 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, 0. So the period equals to 3 here, right? I get a period, right? So after this period, I got repetition of the numbers, right? So then I write this number x as 0 modulo 3, right? So means x is a multiple of 3, and this also I can write it as 1 modulo 3 if I can write this way. So it says that x is a multiple of 3 plus 1, right, as a remainder, right? So generally we write this thing as x equivalent to or x equals to y modulo 3 or modulo k, you can write, in fact. So which is basically the number x you can write as 3k plus y for k belongs to some z, right? Any integer number. So this is the expression to write any numbers in terms of modulo form, and this is the exact number you can represent in this way, right? So also notice that the periodicity of modular arithmetic. So here, from here, we understand what is the periodicity here, right? Where the period is. So if I write x equals to y modulo n, means for example, if I write x equivalent to y modulo 3, just this example, this means y can be, y belongs to 0, 1, 2, right? And if I write x equivalent to y modulo n, so that means y can be 0 up to n minus 1. So this is just how we do the modular arithmetic. So I'm giving a 5 minutes break, and we'll come back with the implementation of QFT, because we need to identify this periodicity. This will not be there. This with what modulo, what periodicity, only this number will be given, right? So this is, I won't solve the full derivations of source algorithm because the pseudocode is already given and implementation is not possible currently. but at least how to find out the periodicity. So we have the Fourier transform tools, and we'll understand how this tool is designed, right? And with this, I stop here for 5 minutes and we'll come back at 4:10. If you have any question, please feel free to put in the chat box. And I thank Professor Pillai sir. He introduced our book. So those who are beginners to the subject, and based on, because I was taking the most of the QT courses, QT-01 to 5, and people are asking for a basic material because many of them are from non-physics background, and this is one thing that we have tried. So you may have a look into this copy if you want. There are many other good resources. Please look at those with a similar pace. Please feel free to put your questions. Okay, shall we start maybe? Mm, audible? Can someone confirm? And my screen is visible?
Yes, sir, audible.
Yeah, thank you. Yeah. So we were talking about the source algorithm, and we introduced what the modular architecture arithmetic is. And now the most important part is the quantum Fourier transform. And beginning, I just shared the context between the classical and quantum part. Mathematically, they are the same thing, but technology-wise, how they are implemented are very, very different. And now we'll see how this QFT is actually implemented on a quantum computer, or the how the operator is designed. Okay. So QFT is effectively what we learned is a change of basis, right? Change of basis from, so for now it's a change of basis. Quantum Fourier transform, what we will do, change of basis from computational basis. Computational basis means this Ket0, Ket1 representations, right? The information is represented in Ket0, Ket1 or Ket0001 and so on, right? To the Fourier basis. Now we'll understand what Fourier basis means in quantum computing. So first let us look in the 1 qubit picture. So in 1 qubit, the computational basis are Ket0 and Ket1. This is our computational basis. And the Fourier basis is plus and minus are the Fourier basis. So how does it look like in the Bloch-sphere? So in the Bloch-sphere representation, so I think in previous lectures QT1 and so this was very much demonstrated. Previous QTs, like say for example, this is your Ket0, this is your Ket1, right? What you need to do is to apply a unitary matrix, right? Unitary matrix such that our information sorry for this bad drawing, such that our information is either say here or it is say here, and this is our plus basis, this is our minus basis, right? This one. So then this particular plane is this particular plane we call it a Fourier plane, right? Fourier plane or the Fourier space or subspace, whatever you say, right? Where this vector and this vector together, right, creates this entire plane. So typically in Bloch sphere, these orthonormal bases are represented in opposite polarity. In Cartesian coordinate system, this way we denote the orthonormal vector in Cartesian system. In Bloch sphere representation, the opposite polarity means 90 degrees. Okay. So this is just a geometry. Just for example, here in this particular case, ket0 and ket1, you can see they are opposite polarity. Though they are in the opposite pole, but they are typically orthonormal vector. That means dot product between 0 and 1 equals to 0, right? So can anyone tell what is this unitary matrix such that I get 1, 2 plus, I get sorry, I get 0, 2 plus, and I get 1, 2 minus. So what is that unitary matrix? Can anyone say for the 1 qubit case? This is very easy question. What is the unitary matrix that you need to apply such that you get plus from 0 and minus from 1? Yes, the answer is the Hadamard matrix. So Hadamard matrix itself is the quantum Fourier transform for 1 qubit, single qubit. Yes, exactly. So Hadamard gate itself is the quantum Fourier transform for single qubit, because we need to reach to this plane here. Earlier, our quantum state was somewhere here. Maybe I can use different kits for the time being here. Sorry, what is happening? It was here, but now this vector will come here in this particular plane, right? Hadamard gate. So everyone is correct. So zeroth basis to, like, because the Hadamard gate is your the 1 1 1 minus 1 is the matrix by normalized 1 by square root 2, and if you apply 0 with the Hadamard matrix, that is 1 1 1 minus 1 times the 1 0, and this is basically equals to 1 1 normalized by square root 2 both side, and 1 1 means basically ket 0 plus ket 1. So this is also known as the superposition gate, right? Similarly, if you do the mathematical computation for 1 with the Hadamard, you will be getting, say, 0 minus 1 by square root 2. This particular state we call plus state, and this particular state we call minus state, right? And so this is for 1 qubit particular case, right? Now, for n qubit, so so what are the first we need to know the computational basis, and then we'll see how to create the Fourier basis. So the computational basis for n qubit, for 2 qubit ket 0 ket 1, for 1 qubit, for 2 qubit it is 0 0 0 1 1 0 and 1 1 are the basis, right? Orthonormal basis or computational basis, right? For 1 qubit, for 2 qubit, right? And for n qubit, I will have how many bases? I'll have all 0, many such zeros, to many such ones. But what is the length of this? Length will be, if I have n qubits, I'll have 2 to the power n basis states. How many such vectors? 2 to the power n basis states. Right. So suppose n equals to 2 to the power n number of bases, right? Now we need to know how to create the Fourier basis. If we know the computational basis, then we are done. So we'll go a bit slow because all these are mathematical details. I'll request all of you to, if you can write with me, that will be much clearer. Okay. Okay. We'll derive certain things and we will assume certain things. So definition of this thing is the x tilde. Suppose this is the Fourier transformed vector. where I apply a quantum Fourier transform, which is typically a unitary matrix. You can also write it as U of f Fourier unitary matrix times the vector x, because this particular computational basis is denoted by, say, ket x. Okay. And if you apply the quantum Fourier transform on the ket x, you get ket x tilde, where this ket x tilde are the Fourier basis. And this is the computational basis. Now, this is equals to, this definition of UF mathematically is 1 upon a square root 2, because this transformation is done with a kernel, right? So what is that kernel function? 1 by square root 2, 1 by square root n. So the light needs to increase. Then summation, suppose y equals to 0 to n minus 1 e to the power 2 pi I x times y divided by n get y, right? This is just the definition of the kernel times get x, right? So this is how the things happen, right? So this is the kernel function for Fourier thing, because this is very simple. When we did in UG classes, we know 2 pi I 2 pi I, the imaginary number, into xj by number in number of discrete Fourier terms, right? And the basis vector itself, right? This is very simple one. Now we'll see how this is implemented on a quantum machine. So we'll currently see another definition of Hadamard matrix now. So suppose for 1 qubit case, and then we'll extend to multi-qubit. So for n 1 qubit, so n equals to 2 to the power little 1 equals to 2, right? Two bases we have, ket 0 and ket 1. So if you do QFT on ket x, which is 1 upon square root 2 y equals to 0 to minus 1 e to the power 2 pi I x into y by n equals to 2, right? Ket y, and this entire story into ket x, right? So how many possibility of y is here? 0 and 1, two bases, right? So it will be 1 upon square root 2 e to the power 2 pi I. It may feel bit boring, but this is important because many of you will be teaching in the class. So you can do more elaborations and all. So I'm just putting the mathematics. You can you can minimize or maximize this part. So y will take two values. One is 0, another will be 1, right? Right. So if this is the case, then so first part will be, this part will be equals to 1, right? Because e to the power 0 is 1. So get 0 plus e to the power I pi x, I pi x get 1. Right. So this is the thing we have, right? And we can you prove now? Can you prove that QFT of 0 equals 2 plus, right? From this using this equation, but from definition, right? So now QFT of 0 is 1 square root 2 ket 0 plus e to the power I pi. Now x will be equals to 0, right? Get 1, that is equals to 1 by square root 2, get 0 plus get 1, which we say it's plus state, right? Similarly, QFT of 1 will be 1 upon a square root 2, 0 plus e to the power I pi 1 times 1, which is 1 upon a square root 2, 0 minus 1, which is the minus state. It is not that Hadamard gate itself is QFT matrix, because these two results are suggesting that yes, this is the Hadamard gate, which is the quantum Fourier matrix for 1 qubit gate that yields the result plus and minus. But here, if you see, this is the generic definition of Hadamard gate super, or the for 1 qubit. So this is a generic definition, right? Which is dependent on particularly x, right? So this is another way of writing the Hadamard thing on the Fourier matrix. So I'll come to this definition again. Like I'll come back here. Okay, this is important. Now we'll be doing. Suppose we want to do note on the note on multiple qubit things, right? Suppose we have 3 qubits, right? So what's the definition? The definition is x tilde will be 1 upon a square root 8 summation of y equals to 0 to 7, right? And e to the power 2 pi I x into y by 2 to the power 3 get y, right? And here get y can take values, right, from 0, 1, 0, say 0, 1, 1, any 3 values, like for example 1, 1, 1, right, etc. Okay, so this summation typically, in binary representation, there is a binary representation. So you can also write this get y as y1, y2 up to yn number of bits, little n number of bits, as many number of n qubits. If there are n qubits, so this get y can be represented as y1, y2, y3, yn, where this each yi can be a binary variable 0 or 1, right? That is then this get y it is a mapping of this binary string up to n points, where it can take either 0 or 1, any position, but there are n number of digits, right? So this is just a representation of this basis in binary settings, right? And also sometimes this this summation in the binary notation, that y 0 to 7, this thing also sometimes in some books you will see as 0 to 7 also can be written as binary variable summation, say y1 0 to 1, then summation y2 equals to 0 to 1. So this individual y1, y2, y3, so on up to summation yn equals to 0 to 1. This many variables times the particular representation, say all these values y1, y2, y3, and so on, right? So yn, right? So if I start with 1, you can write as 1. Okay. So so this is how just representations for the basis point in binary settings. But now let us see the big picture. Okay. So this x tilde, now the evolved basis, right? The Fourier basis representations can be written at 1 upon square root n, and in summation of y equals to 0 to n minus 1 e to the power 2 pi I x time y by, I can write n, or I can also write n equals to 2 to the power n, anything, get 1, get y, right? So, so I'm just writing the kernel part. So n equals to 2 to the power n, right? Suppose. And this y, suppose is written in binary string y1, y2 to up to yn. This is the binary representation of the this particular variable y, right? So any binary representations, we can also write it as 2 to the power n minus 1 y1 plus 2 to the power n minus 2, just in this particular form, right? Any number we can, like if there is a decimal number 741, how we write? 7 into 100 means 10 square, plus 4 into 10, right? Plus 1 into 1, 10 to the power 0, right? 10 to the power 1, 10 to the power 0. So this way we represent a decimal number. Similarly, any binary number you can expand in this way, plus 2 to the power 0 by 0, right? Or yn, right? So this is how we represent binary numbers, right? So now y, you can write it as k equals to 1 to n yk. This is the same thing I'm writing, yk 2 to the power n minus k. And this is equals to sum over k equals to 1 to n yk 2 to the power n by 2 to the power k. Just breaking this minus part in the denominator, right? And then this x tilde will become 1 upon square root n summation over y equals to 0 to n minus 1 e to the power 2 pi I x. And then for y, I can write the binary representation yk by 2 to the power k. And in the denominator, there was a 2 to the power little n. In the above, there is a 2 to the power, this part you can cancel out, times y1, y2, dot, 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 y, right? So this part I can write it as, now next line is extremely critical, because uh, in the recursive implementation we'll be trying to do, still it's just a product implementations, right? Just a summation representations, but this summation representation will do as a sum of product, right? Sum of product. So this is a sum term, and we can write this sum term as 1 upon a square root n summation of y equals to 0 to n minus 1, then product of k equals to 1 to little n, right? And because e to the power sum, right? Suppose what this means, e to the power, suppose there is x plus y, right? So I can write that e to the power x into e to the power y. If they are commuting just simple scalar quantities, e to the power x times e to the power thing. So that means e to the power sum of something xi can be written as product of e to the power of that, right? So this sum will come as a product in the beginning. If it is plus here, it will come as a product here, right? E to the power this into e to the power that, right? So this sum outside this e to the power comes as a product. So then this will become e to the power 2 pi I x into yk divided by 2 to the power k, and y1, y2, 2 up to yn. This is a critical step, and this particular is the sum term, and this is the product term, right? Sum of product, right? And this is what we call the tensor product. This is what we want for circuit design for recursive implementation, tensor product, because sum of product is the tensor product. So, and this first hand part, we just know this is the sum of so on. Y1 equals to 0 to 1, y2 equals to 0 to 1, so on up to yn equals to 0 to 1, right? This is the binary breakup of this first term, right? So what effectively is done, what we are doing here to here, we'll do certain things, swap the order of the product and the sum, and bring in the terms, separately, which is called the tensor product. So I should not write here directly, but this is the tensor product we can do. And then what happens is, once you break the bigger sum into small sum and swap between sum and product, you can write this x tilde intelligently in this way: 1 upon a square root n, which will go to outside. First, it will be kid 0, because we are breaking this part. This each kid y1, y2 to yn can take either 0 or 1. So the first qubit will be kid 0 times e to the power 2 pi I x by 2 to the power 1 kid 1. Tensor product with kid 0 plus e to the power 2 pi I x by 2 square kid 1. Tensor product with so on 0 plus e to the power 2 pi I x times 2 to the power 3 kid 1. Tensor product so on up to 0 plus e to the power 2 pi I x by 2 to the power n kid 1. This is an important breakup, right? This is for the nth qubit. So what I have done, I have a big function. I have boiled it down to n number of functions, where each individual part looks like certain Hadamard. If you look at this picture, right? So it looks like a Hadamard, but every time there is a coefficient 2, 2 square, 2 to the power 3, 2 to the power n, right? So there is another phase part. So what is happening, this equation is that we are using the architecture of qubit, right? For a recursive implementations here, using the tensor product property of the multiple composite quantum system or multiple quantum system. So we can build a circuit. So this will go to first qubit, second will go to second qubit, third qubit, and nth qubit. So we can build a circuit for this similar to what we did with Hadamard gates. What we did with Hadamard gates. Hadamard gates plus there is a complexity, and that complexity is with the 1 by 2 to the power n in phase, right? So this is the additional part, because otherwise if there is no 2 pi ix, if you see the beginning definitions of Hadamard gate, so here this is e to the power I pi x, right? Done. But in the actual implementation for n qubit system, composite quantum state system, I can see there is a phase factor coming every time, 2 square, 2 to the power 3, 2 to the power n, right? So this is the additional complexity coming into picture. What is right? So this k takes original computational basis, and the basis was x1, x2 dot 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 xn. Sorry. Sometimes there are issue with the writing pad, even with the iPad. Right, where such each xi can take a binary value like 0 or 1, right? And this is a beautiful thing because you can write this entire tuple or the vector as x1 quantum state tensor product with x2 tensor product with x3, right? So on up to xn. What did I say? Just by example, if there is a say vector, right? Column vector, orthonormal vector like this. This is equivalent to, or this is same as O tensor product with O tensor product with 1, right? And if you do the quantum Fourier transform on this, what you get is mathematical function x tilde, which is 1 upon square root n, 0 plus e to the power 2 pi I. Even after this, some of you may feel difficulty, right? So during my PhD, I studied 4 years. I still did not understand what quantum Fourier transform was saying, right? And somehow I found this mathematical thing from various resources, and I thought this is a good explanation. But it is good if you have difficulty, then you will do your own way of understanding QFT and how not only QFT, other mathematical transform also you can try. If you understand this design, you can think of, suppose you want to implement Laplace transform in quantum, right? And you don't have to look for who will implement Laplace transform for your quantum circuit. First, you need to identify, okay, what is the unitary equivalent of that mathematical transform? Now, can I implement that unitary transformation matrix on a quantum computer, right? And this is the way I'm describing each and every step and the philosophy, how a big equation is split into small part, and that in tensor multiplications, right? Tensor product, and how they will be implemented, right? I'll show the implementations part tomorrow, and maybe possible today. I shared the circuit. If possible, you can have a look. So 0 plus e to the power 2 pi I x by this 2 square part, get 1 tensor product, so on, right? And the final term is 0 for the nth qubit, e to the power 2 pi I x by 2 to the power n, get 1, right? So now individual basis x1, x2, x3, how it is changed to this particular basis set, this basis set, right? For example, if I ask you to, if my basis is say 101 is the computational basis, that is QT-05, right? What will be the quantum Fourier transform of this particular basis, right? So you can do QFT on this x, that is the x tilde for this particular basis, and you can do 1 by square root 8 because there are 3 qubits, so n, capital N equals to 2 to the power 3 and small n equals to 3, right? So 1 by 8 and 0 plus e to the power 2 by I 5 by 2, get 1 tensor product with 0 plus e to the power 2 by I 5 by 4, get 1, so on. And the last term will be 0 plus e to the power 2 pi I 5 by 8, get 1, right? So only there are 3 terms. So this, and this will be the three particular terms for 3 qubit, right? Now, now the design part, right? So on the right hand side, if we see, so what are the phase component coming? One is the e to the power 2 pi I x by 2 to the power 1 plus if I look at this 2 pi I x by 2 square, not factorial, plus so on, plus 2 pi x by 2 to the power n, right? And all say ket0, ket1, whatever it is, right? So if I take the product of all the terms, right, because this is a tensor product, and if I could expand this thing, right, so what are the things x tilde contains? If I look at, so the first product will be 0 times 0 times 0. How many 0 will be there? There will be n 0. So the first term, if I could actually break the final equation, these equations, right? So first term will be this multiplied with this, multiplied with so many this, and I'll multiply with this one. So the first term here, it will be all 0, right? Right. The second term will be, there will be 1 e to the power of all 0, and e to the power 2 pi I x by 2 to the power n, all 0, and last one will be 1, right? Third one will be e to the power 2 pi I x by 2 to the power n minus 1, all 0. Last one will be 1, and there will be another 0, right? So on. And then if I look at the final term, right? So the final term will be, so because each qubit went from ket xk to this ket0 plus e to the power 2 pi I x by 2 to the power k for kth qubit, right? And this propagation of the qubit from xk normal computational basis to this particular basis, the last information is this one. This is the for nth qubit, right? Which is e to the power 2 pi I x by 2 plus x by 2 square plus so on up to x by 2 to the power n, and the all qubit will be 1 1 1 1, so on, last one will be 1. So this will be the final qubit representations, right? So this is the possible basis set if I expand all the terms, right? And before designing the final circuit, let us again go back to one basic thing. So how to design the final circuit. So the phase is qubit dependent and need to add more circuit component with more ones. So if I look at from this side to this side, so this is, you have to do nothing, right? First part. But second part, there is a single phase term. Third part, there is a more phase term. In the last nth qubit, there is so many phase component, right? So if I go from top to bottom, how many phase component I am adding? So there are many phase component I have to add, right? So there are when we'll implement, so there are two major part. One is apply Hadamard. Apply Hadamard. So if I apply Hadamard to xk, kth qubit, right? So what will happen? Two consequence can be there. One is if xk equals to 0 and if xk equals to 1, because these are the two possible states, right? Achha, there is one question. If we apply Hadamard gate, we get these outputs. No, there is a fetch term, right? So that is, so I was telling how Hadamard gate will create this kind of interference pattern. No, right? Only the superposition state you can create. So this pattern, I will see how we can create. There is one question, sir. Is it x or x1, x2, x3, so on? Where? With it inside, right? So yeah, this should be x1, x2. You are correct, so on, right? Yeah. Thank you for telling me. That means you are following each and every steps. Thanks for this. So if I apply Hadamard to the state xk, and if xk is 0 or 1, if it is 0, then I'm getting the 0 plus 1 by square root 2, that is the plus state, right? And if it is 1, then I'm getting 0 minus 1 by square root 2, that is minus state. This is the two possibilities, and I can write in a write these two possibilities in a compact way, and that is 0 plus e to the power 2 pi I xk by 2 k to 1 by square root 2. So I got the first term, plus 2 to the power 1. So if I apply only Hadamard gate to the first qubit, I am done, right? Because Hadamard gate has the possibility, depending on the particular qubit state, whether 0 or 1, it can create this particular state. So if you take x equals to, say, for example, if in this equation, if xk equals to 0, you get C, it is 1. And if it is xk equals to, suppose, 1, you will get minus 1. So accordingly, you will get plus state and minus state, right? So these are the easy verification. And second, I have a most important thing, is the U rotation gate. U rotation gate. So U rotation kth on kth qubit, if that qubit state is xj, is e to the power 2 pi I by 2 to the power k xj kth xj. What is that? So if xj equals to 0, so e to the power 2 pi I 2 to the power k xj, that is 0 times ket 0. So it will be ket 0 only, because this entire part, if it is 0, so will be 1, and this part will be ket 0 only, right? So 1 times ket 0 is ket 0. And if xj equals to 1, then e to the power 2 pi I by 2 to the power k xj ket xj. So this part will be 1 and this part will be 1. So it will be e to the power 2 pi I by 2 to the power k to 1. Okay. So we can write in a compact way that U rotation k gate equals to 1, 0, 0 e to the power 2 pi I by 2 to the power gate. This is known as the U rotation k gate, right? But this is not readily available. You have to prepare this. Okay. For example, R theta gate, right? R theta phase gate is basically 1, 0, 0 e to the power I theta, right? So, I mean, this is how you can create this one. This is also another thing, but you can write, if you have a phase gate with kth rotational coefficient, so this is equivalent to 1, 0, 0 e to the power 2 pi by 2 to the power k, right? And so what this means, if I look at this particular equation, so if the qubit state is ket 1, then it applies phase e to the power 2 pi I by 2 to the power k, to k particular qubit, right, to that state ket 1. And if the state is 0, it does nothing, right? If the state is 0, then it does nothing to that qubit. But if the state is 1, it applies a phase of 2 pi I by 2k, and that is represented with a matrix 1, 0, 0 e to the power 2 pi I by 2 to the power k, right? So so if you see the picture, actual Qiskit implements in a reverse way. Okay. uh, so for various reason, but the way we implement, why it is happening, sure. So if I have a qubit like this, quantum circuits, say this is my x1, this is my x2, this is my x3, x4, and so on to xn, n number of qubits. And this is my input states, for example, gate x1, gate x2, gate x3, gate x4, gate xn is my input, for example, in the circuit, right? And I need to apply a Fourier transform on it such that I get a Fourier transform evolved state, right? Evolved quantum state. So actual circuit, if you see, if you look at, you will see like this. So first they will apply a Hadamard here, right? And then they will apply a U rotation here. U rotation with a factor of 2 to the power 1, right? Then this is controlled with the second qubit. Then there is a U rotation, U rotation. This is with k equals to 1. This is with k equals to 2. Rotation with controlled with 2, right? So why I am implementing these things is because if you look at the previous approach here, so I was applying nothing to the first thing. Secondly, adding a phase factor to the second qubit condition to the state 1. Third, I will apply 2 phase factor and condition to the second last second qubit, second last qubit to be 1. So on at the last qubit, there will be many such phase factor. In the actual implementation, you just need to consider that your last qubit is just this one you have to consider as a first qubit, right? This is just for implementation reason. I need to connect it to power cable because otherwise it will go off. Implementation wise, if we look at, this is the first input, right? First qubit for us. So in the first qubit, we'll only apply the Hadamard gate, nothing else. Second qubit, I will have a Hadamard and another one rotation gate. So in the last qubit, there will be one Hadamard and many other rotation gates and all. So up to basically k equals to n. That means 2 to the power, the factor is 2 to the power nth phase factor. There will be a phase gate to the last qubit. So so because stepwise, if you look at the first step here, step 0 is x1, x2 to up to xn. Then step 1, it is get 0 plus e to the power 2 pi I by 2 x1 get 1 tensor product with the x2 up to xn, because this is a x2, I have only applied one rotation gate, right? And rest this is your first step, you have applied the Hadamard. Sorry. Step 2 and so on. So you can calculate how it is. So tomorrow I'll continue from here and I'll demonstrate an implementation, detailed implementation in Qiskit such that you get familiar with this. And then I'll continue the quantum phase estimation and then the HHL algorithm. So with this, I'm concluding today's session here, and please feel free to ask me any question if you have. So I'll be happy to answer. Sir, you might take any questions, or shall I leave or something?
Thank you so much, sir, for this wonderful session. And thanks to all the participants for making it meaningful. Thank you so much. Tomorrow we will meet at same time. Thank you.
Thank you so much.
Thank you.